Let's talk about ellipse. So what is an ellipse and how is it related to circle and parabola? An ellipse, which you can see in our illustration, is the set of all points on the plane whose distance from two fixed points, which are f sub 1 and f sub 2, add up to a constant. Now, if you can still remember, a circle is a set of all points which are equidistant to a fixed point called the center. Now, in a circle, we have one fixed point. For an ellipse, we have two fixed points. Now, here are the parts of an ellipse. Let's start with the center. So, just like a circle, an ellipse also has a center, which is again the point in the middle of the ellipse. An ellipse also has foci. Now, what are foci? Foci is the plural form of focus. So, foci, or the foci of an ellipse, are denoted by f sub 1 and f sub 2. Now, as you can see in our illustration, just like the focus in the parabola, the foci of the ellipse are inside of our ellipse. Now, foci are still special points with reference to which any of a variety of curves is constructed. The next one, we have the major axis, which is the line segment through the foci and across the ellipse. Now, as you can see in our illustration, the major axis is the longer axis or the longer segment between the two segments that you can see inside our ellipse. On the other hand, we have the minor axis, which is the line segment across the ellipse through the center and perpendicular to the major axis. As you can see, it is the smaller or the shorter axis or segment in our ellipse. In an ellipse, we also have vertices, which are denoted by v sub 1 and v sub 2. Now, the vertices are the endpoints of the major axis. Now, look at the illustration. Again, the vertices are the endpoints of the major axis. The term vertices is the plural form of vertex. Again, they are denoted by v sub 1 and v sub 2. Now, we also have the co-vertices, which are denoted by v prime sub 1 and v prime sub 2. Now, if the vertices are the endpoints of the major axis, the co-vertices are the endpoints of the minor axis. Again, denoted by v prime sub 1 and v prime sub 2. Another part of an ellipse is the semi-major axis. It is the distance from the center to the vertex or to one vertex, which is denoted by A, which you can clearly see from our illustration. Now, the semi-major axis is also half of the major axis. We also have the semi-minor axis, which is the distance from the center to the co-vertex, which as you can see, it is denoted by B. Again, semi-minor axis is also half of the minor axis. The next one, we have the focal length. So again, just like a parabola, we'll also have a focal length because we have foci. So the focal length is again the distance from the center to the focus or to one focus. Now, if the focal length is denoted by A in our parabola, in an ellipse, the focal length is denoted by C. Now, the last part of an ellipse is the latus rectum. Again, just like a parabola, we also have a latus rectum. A latus rectum is the chord of the ellipse through its one focus, perpendicular to the major axis and parallel to the minor axis. So if we have two foci, we also have two latus rectums for our ellipse. Now, if in a parabola, the formula to get the latus rectum is 4a, in an ellipse, the formula to get the latus rectum is 2b squared all over a. So those are the parts of an ellipse. So if a parabola can either face upward, downward, to the right, or to the left, an ellipse can also be vertical or horizontal, depending on the orientation of its major axis. If its major axis is vertical, then the ellipse is vertical. If its major axis is horizontal, then the ellipse is horizontal. So those are the two orientations of ellipse. The orientation of an ellipse depends on its equation. Now, if the major axis of an ellipse is horizontal, the equation in standard form is x minus h squared all over a squared plus y minus k squared all over b squared is equal to 1. On the other hand, if the major axis is vertical, the equation in standard form is y minus k squared all over a squared plus x minus h squared all over b squared is equal to 1. Now, what can you notice about our equations? Or what do you think is the difference between the two equations? If the major axis is horizontal, a squared is under x minus h squared. On the other hand, if the major axis is vertical, a squared is under y minus k squared, y. Because again, a is the length of the semi-major axis, which defines the orientation of our ellipse. So in these equations, h is the x-coordinate of the center, k is the y-coordinate of the center, a is again the semi-major axis, and b is the semi-minor axis. So those are the standard form of equations of an ellipse. Now let's have an example on how we can write the equation of an ellipse given some points or parts of our ellipse. For example 1, we have to write the equation of an ellipse in general form centered at the origin or 0, 0, and the major axis is horizontal with length of 8 and the minor axis measures 4. Then we have to sketch the graph after writing the equation. So, from our given, what will be our first step? Or which values will be useful for us to write the equation? Again, the major and the minor axis are already given. The major axis is equal to 8 and the minor axis is equal to 4. And again, according to our problem or according to our given, the major axis is horizontal. Therefore, we are going to use x minus h squared all over a squared plus y minus k squared all over b squared is equal to 1. Again, because the major axis is horizontal. So let's assume that our ellipse is horizontal. Now, since the major axis is equal to 8, therefore, the value of a, or the semi-major axis, is equal to 4. Again, a, or the semi-major axis, is half of the major axis, which is 4. Same with the minor axis. The minor axis is equal to 4. Therefore, b, or the semi-minor axis, is equal to 2. Again, half of the minor axis. Now, by just looking at the values of a and b, we can now write the equation of this ellipse. Again, it is just centered at the origin or 0, 0. Therefore, we will have x squared all over 4 squared, that is x minus 0 squared, that is x squared, all over a squared, that is 4 squared, plus y minus 0 squared, that is just y squared, all over b squared, that is 2 squared, is equal to 1. Now let's evaluate 4 squared and 2 squared. We will have x squared all over 16 plus y squared all over 4 is equal to 1. Now, when we're writing the general form of an equation, we have to eliminate all the denominators. What are we going to do to eliminate the denominators in our equation? We are going to multiply both sides by the least common denominator, which is 16. So if we're going to multiply both sides by 16, we will have 16 times x squared all over 16, that is x squared, plus 16 times y squared, that is 16y squared, over 4, that is 4y squared, is equal to 1 times 16, which is 16. So let's transpose positive 16 to the other side of the equation. So the general form of equation for this ellipse is x squared plus 4y squared minus 16 is equal to 0. Now that we have written the equation for our ellipse, we can now proceed to graphing. Again, the center or the coordinates of our center are already given, which is at the origin. So we can plot the point at 0, 0. The next one, we already have our A, which is equal to 4. Again, A is the semi-major axis, or half of the major axis. And again, according to our given, our major axis is horizontal. Therefore, we can count 4 units to the right and to the left of our center. So there we have the endpoints of our major axis, or there we have our vertices. The next one we have B is equal to 2, which is again the semi-minor axis. Therefore, we can count 2 units upward and downward from our center. So there we have our co-vertices. Now, by just looking at our points so far, we can see the orientation or the behavior of our ellipse. But we can clearly graph our ellipse using the focus and the latus rectum. Now, how can we get the coordinates of our focus? Or again, how can we get the focal length, which is denoted by C? We can use the Pythagorean theorem. Now, if you can still remember, the Pythagorean theorem is C squared is equal to A squared plus B squared. But when it comes to ellipse, again, the longest segment among the 3 segments is A. Therefore, for ellipse, we apply A squared is equal to B squared plus C squared. Because again, A is the longest segment among the 3 segments. So let's just plug in the values to get C, which is again the focal length. So we have 4 squared is equal to 2 squared plus C squared. That is 16 minus 4 is equal to C squared. Therefore, we have C is equal to the square root of 12, or approximately equal to 3.5. Therefore, our focal length is 3.5. So to get our foci, we count 3.5 units to the right and to the left of our center. So there we have our foci. Now again, our latus rectum will pass through our foci. So to get our latus rectum or the length of our latus rectum, we're going to use the formula 2b squared all over a. Again, b squared is 4. So we will have 2 times 4 all over 4, or we have 8 over 4, or is equal to 2. Therefore, our latus rectum measures 2 units. So we have to count 1 unit upward and downward from our focus. So there we have the endpoints of our latus rectum. So with the help of our foci and the latus rectum, we can now clearly see the orientation and behavior of our graph. So we can just connect the endpoints and the vertices of our ellipse, and there we have the graph for x squared plus 4y squared minus 16 is equal to 0. So that is how you graph the equation of an ellipse. Next, for our example 2, let's do it the other way around. This time, we have to find the coordinates of the center, the vertices, the co-vertices, foci, length of the major axis, minor axis, and the latus rectum of an ellipse given the equation 25x squared plus 9y squared plus 50x minus 36y minus 164 is equal to 0. Now, how can we find all the parts of our ellipse given the equation in general form? Again, just like what we did in circle and parabola, we first have to convert this given general equation or general form of equation into its standard form. Again, how can we do that? By applying the completing the square method. So to apply the completing the square method, our first step is to transpose the constant term to the other side of the equation and group all the terms with the same variable. Therefore, we will have 25x squared plus 50x plus quantity 9y squared minus 36y is equal to positive 164. Again, move the constant term to the other side of the equation and group all the terms with the same variable. Now, as you can see, our first terms have a numerical coefficient that is more than 1. As you can see, we have 25 and 9. So let's factor out some terms first. So we can have 25 times x squared plus 2x, and we can also have 9 times y squared minus 4y. So those are the factors. Now, as you can see, we only have a numerical coefficient of 1 for x squared and y squared. We can now complete the square. Again, by using completing the square, we first get half of the first degree term or the second term. For x squared plus 2x, we have 2x divided by 2, that is 1. 1 squared, that is plus 1. Same with our next part, we have y squared minus 4y. Half of negative 4 is negative 2. Negative 2 squared is positive 4. So we will have 9 times y squared minus 4y plus 4 is equal to 164, and don't forget to add the third term. But this time, since we factored out some terms, we have to multiply 25 times 1 first before adding, and also 9 times 4. So we have plus 36. Again, add all the terms to our constant term. So we have 164 plus 25 plus 36. So let's proceed to getting the factors of our perfect square trinomials. For the first one, we have 25 times the factors of x squared plus 2x plus 1 is x plus 1 squared. For the next one, we have plus 9 times the factors of y squared minus 4y plus 4 are y minus 2 squared. Therefore, we have 9 times y minus 2 squared is equal to 164 plus 25 plus 36, that is equal to 225. Now again, in the standard form of equation of ellipse, the right-hand side of the equation or the constant term must always be equal to 1. So how can we eliminate 225? Again, we can divide both sides of the equation by 225. So we can get 1 as our constant term. So by dividing it, we can get 25 times x plus 1 squared divided by 225, that is x plus 1 squared all over 9, because 25 over 225 is 1 over 9. For the next one, we have 9 times y minus 2 squared all over 225, that is y minus 2 squared over 25, because 9 over 225 is 1 over 25. Then again, at our right-hand side of the equation, we have 225 divided by 225, that is equal to 1. So now we have the standard form of equation for the ellipse. If you're going to look at the denominator of our standard form, you can see that 25 is bigger than 9. So what does it mean? 25 will be our a squared because that is bigger. And in this case, a squared is under y minus 2 squared. Therefore, we can conclude that our ellipse is vertical. So, the standard form of the equation for this ellipse is y minus 2 squared all over 25 plus x plus 1 squared all over 9 is equal to 1. We can now find the missing parts of our ellipse. So again, we already have the standard form of equation for this ellipse. We can clearly see that the center is at -1, +2. Again, that is HK. So let's plot the point for our center. Again, we have -1, +2. Now again, by just looking at our equation in standard form, we can clearly conclude that our ellipse is vertical. So we can get A from our a squared, which is 25. Again, a is the semi-major axis. If we have a squared is equal to 25 from our standard form of equation, let's extract the square root of both sides. Therefore, a is equal to 5. Now, if that is the measure of our semi-major axis, we can now count 5 units upward and downward from our center. Again, it is vertical, that's why we're going to count upward and downward. Therefore, there we have the endpoints or the vertices of our ellipse. So, v sub 1 is at -1, +7, and v sub 2 is at -1, -3. Those are our vertices. We can also get our co-vertices by using b squared. Again, b squared from our equation is equal to 9. Therefore, if we're going to extract the square root of both sides, b is equal to 3. So we can now count 3 units to the left and to the right of our center. Again, B is the semi-minor axis. So there we have the endpoints or the co-vertices of our ellipse. So V prime sub 1 is at 2, 2, and V prime sub 2 is at -4, +2. Again, those are our co-vertices. For the next one, we have C. Again, we're going to calculate the measurement or the length of our C, or the focal length. Again, by using the Pythagorean theorem. But again, A squared is the largest one, or the longest one. So we have 5 squared is equal to 3 squared plus C squared. So we have 25 is equal to 9 plus C squared. Transpose 9 to the other side of the equation, we will have 25 minus 9 is equal to C squared. 16 is equal to C squared. Let's extract the square root of both sides. Therefore, C is equal to 4. So the focal length is equal to 4. To get the foci, we can count 4 units upward and downward from our center. Therefore, the coordinates of our foci are -1, +6, and -1, -2. Those are our foci. Lastly, we have to get the length of our latus rectum by again using the formula 2b squared all over a. Again, our b squared is 9. Therefore, we will have 2 times 9 all over 5, or that is 18 over 5, or equal to 3.6. Therefore, our latus rectum measures 3.6. So again, divide it by 2, and we have to count 1.8 units to the right and to the left of our focus. So there we have the endpoints of our latus rectum. So now that we can clearly see the behavior and orientation of our graph, we can now connect the endpoints and vertices of our ellipse. So there is the graph for 25x squared plus 9y squared plus 50x minus 36y minus 164 is equal to 0.